everyone, this is just Mr. Tukin, and we're going to spend a little time analyzing piecewise functions. We're going to go over a few things. This has a very broad topic. We're going to start pretty basic with it. We're going to spend a lot of time interpreting. Now, before we get started on this, one thing that I always kind of focus on is there's a lot of times in math where a teacher might be able to teach you directly, exactly steps to complete certain things, like when we're solving equations, working with a function where it's a quadratic function and there's a formula or there's an equation. There's something we can put concrete to. We can give it to you and say, use this, just follow these steps, and boom, you get the answer. And then there's other times where, my apologies there, what we're going to say is that this is more, I guess, abstract, not concrete. We're going to need to be able to interpret, read, make educational kind of statements regarding what a scenario entails and how it's represented on a graph. That's the biggest thing of a piecewise function. Also, just from the name, if we think of it, you see the word piece, you've got multiple pieces that form to make one function. When we say the word function, just as a reminder, a function on a graph is anything that passes a vertical line test. And for those of you that maybe don't know what a vertical line test is, it's essentially if I have a function, and let's say I've got a function that's a something called a polynomial function, not something we always see or work with, but let's say I've got a function like this. And it is a function, I guess I'm using the word, but this is kind of like representing a polynomial. And the idea is if you take a vertical line and you drag it across the function, it will only touch the function one time. Okay, it'll only touch it in one spot, anywhere along it. So notice how it doesn't double up. That's what makes it a function. So essentially, if we put these things together, you're going to have multiple pieces that form to make one function, meaning it never like overlaps. So for example, something that's not a function would be like anything that makes a circle. If we had a graph that makes a circle, then that's not a function because when we drop a vertical line into it, notice how it's touching in two spots. So that doesn't work. So that's what we're kind of working with here. We're doing piecewise functions. And three main topics we're going to cover here today would be we're going to read a real life situation on a graph. We're going to be able to interpret that graph, and then we're going to work on intervals of change. We'll talk about, hey, where the pieces come together, how they change, or it could be no change. And then we'll briefly just discuss linear versus nonlinear. So we've got this scenario, and I want to kind of put this together here. When we look at this function, some of our graphs, you'll notice, just so we're clear, when we have a coordinate grid, and I'll just kind of sketch it real quick in the bottom over here, we have a coordinate grid. We start with the origin right in the center, but sometimes we'll only look at quadrant one, and that's what we've got here. We've got a graph where we're only looking at basically this quadrant. And if we read it, there's a lot of interpreting. You're going to have to read the graph. You're going to have to read what is the y-axis, what is the x-axis. So we've got this Bob's distance from home and time. So what's happening if time moves to the right? Time is increasing. We're getting further away. So keep that in mind. Then as we go up here, we've got Bob's distance from home. How far away from home is he? And notice these different scenarios where we're going to represent them. We're going to represent them on this graph. We're going to put together, we're going to create a piecewise function. So it says see Bob at home. Well, if this represents his distance from home, if we mark him here, he's clearly further away from the origin, further away from 0. So think about that. That's 0, 0 right there. 0, whatever units, 0 miles, 0 feet, 0 away at 0 time. So if he starts right here, if he starts, then Bob's going to start right at this point. Now, let's think about this. If this had said, see Bob 5 miles from home, if he starts there, then maybe we'd have to turn around and put like a dot up here and say, well, that's about 5. We're saying that's 5 miles from home. So interpreting the graph, the starting position, is usually how you'll start out with a piecewise function. So we've got that. We see Bob at home. Now it says he walks away. That's the first part I want to kind of piece. I could maybe pretend he's doing that and walking away. Maybe I could do this. Well, let's think about this. Bob's on foot. It says he's walking away. Which one would really represent walking? Well, man, doesn't this seem like he's going pretty far away, his distance, right away? Versus this one, You know, if this is the time, right? Look how far away he is compared to right here. At equal time, he's, you know, much closer to home than this one. So since he's walking away, we're going to have a probably a smaller slope. He has gone away, but it's not going to be a huge slope. It's not going to be a huge positive slope because he's not doing anything else except walking. And for the sake of this, I'm going to shrink this down a little bit. I'm going to send this back and say, well, that's just the first part of the piece. We'll say that's it. He just walked about that far. Now, after that, it says, see Bob stop. Well, he stopped, but maybe this could say, see Bob stop for 4 minutes or something. There might even be piecewise functions that have the markings, and we'll show one in a little bit. But see Bob stop. What's important to note is this first one was a positive change. This was slope of positive, and we have areas or intervals of no change. What happens during no change is, well, if Bob stopped, is he getting any further away from home? Ask yourself that. Is he getting any further away from home? But if he did stop, does time stop or does time keep going? Well, the time would continue, but his distance from home would not change. You would have an area of no change, and therefore you'd see a part of a piecewise function where maybe it stops. Now it says after that, Bob starts to run. We have no idea why. He's being chased by a tiger. Who knows? He's late to be somewhere, but he starts to run. And what we have to realize, if this was walking, well then, given that distance, you know, if we're running, we increase our distance, we're going to be looking at a situation where, you know, it has a greater slope. So as we piece these piecewise functions together, we can see those intervals of change. Notice it still is a function. If we ran a vertical line test, none of these have ever crossed each other. No, we haven't doubled up, so we're good. I don't know, nobody's probably ever seen the Back to the Future, but if you have, it's not like you can go back in time. So we're not going to go backwards. And then it says, see Bob hop in a car and drive straight home really fast. Now, the key here is not just that he got in a car. Obviously, the car is faster. But if he went home, what happens to his distance? Oh, yeah, hopefully some of you are saying, well, his distance would go back to 0. So we've got this scenario here where if we piece it together, we can see these things actually coming into place. And that's the purpose of a piecewise function. You're going to need to interpret these intervals of change. Sometimes you're going to be given the graph and then told the scenario. Sometimes you're going to be given a scenario and given multiple graphs, and you have to interpret it. All right, so keep that in mind. So here's another piecewise function. This time, again, we're still looking at quadrant 1, and we've got these actual markings. And notice we want to read the x-axis, we want to read the y-axis. We need to know what we're looking at. We're looking at number of weeks and total coins. And if we read the direction, it says, okay, I'm going to give you the piecewise function, and I want you to pick the scenario that fits the graph. So think about this. Think about number of weeks, 0 here, and there's that. And you can see different kind of changes, those intervals of change, right? Whenever it kind of changes slope, that's an interval of change. And we've got some positive slopes, we've got some negative slopes. So we've got choice A. Choice A says a kid starts out with 5 coins. He doesn't earn any coins for 2 straight weeks, but, and typo here, on the 3rd week, he earns 3 more coins. The next week, he loses a ton of coins, but over the next 3 weeks, he would gain 1 coin back and keep that total number of coins. So we want to say, is this one correct? And then we want to also compare it to choice B. A kid begins with 5 coins. Each week after that, for 3 weeks, he earns 1 coin per week. After this, he saves all the coins for a couple of weeks until losing a bunch of coins in a single week. After this big loss, he makes 1/3 of a coin on average for 3 weeks until finally saving his coins from then on. You might want to pause the video and actually, determine which choice you think is right and why. Well, if you did that, You also might want to spend a little time, like, if you said the y part, then you were able to point out the things that weren't right. Both of them say they start out with 5 coins. And so at 0 weeks, he starts at 5 coins. He doesn't earn any coins for 2 straight weeks. Or in this week, he says each week after that, for 3 weeks, he earns 1 coin per week. Well, from the 0 weeks to the end of the first week, he made a coin according to this graph. And he made that same coin a part of this linear piece. So this one is actually right away going to be choice B, usually, but we still want to point it out. Now, why is this one wrong? Well, he says he doesn't earn any coins for 2 straight weeks. Well, if that's the case, we should have seen a line go horizontal. We should have had an interval of no change. And then it said in the 3rd week, he earns 3 more coins. So we would end up at this same spot, but how we get there is different. The intervals of change are different. This area has a much bigger slope. He makes three coins in a single week. Notice after that, he says that he loses a ton of coins. This one never stated the interval of no change. So he says a ton of coins, and technically that could be anywhere from here to here. I don't know why I started using the pen. Let me get rid of that. But we've got that interval of no change. And so maybe it's to here, who knows? He just says he loses a ton of coins. So it doesn't really tell us how much, but he does. And he does it in 1 week. So we're looking for that change right there instead of this one down here where it says he saves all of his coins for a couple of weeks. That's this interval of no change right here. From then on, it said he would gain 1 coin back and keep that noble, but over the next 3 weeks, he would gain 1 coin back. That's kind of interpretive here where he gains the 1 coin back. But this one's even a little bit better because it says he averages kind of a third of a coin. So it's 3 weeks, but he only makes 1 coin. So a third of a coin, although technically this one's not necessarily wrong there either. But that's why choice B is the better choice here. If we look at this graph one more time, when we talk about positive slope, negative slope, just positive slope, if from left to right, your piece is increasing, then you're looking at a positive slope. If from left to right, your piece is decreasing, you're looking at a negative slope. So you'll have intervals, and they'll label them as like A, B, C, D, and E, and you might be asked, hey, what intervals is there no change? That'd be B and E. When do you have interval of change that is negative or has a negative slope? Well, that'd be C. What about which interval has the greatest slope or the greatest rate of change, or they might say anything, in which case you'd have to choose A. A has a steeper slope. It's increasing more than D. So that's the kind of thing you'll also have to be able to do on the assignment. And finally, just to be clear, which is linear? We'll have linear functions, piecewise functions, and we'll have nonlinear. And you've got some scenarios here. We're looking at a nonlinear right here. There's nothing that's straight. Remember, linear means straight line. This is a purely linear function right there. This one technically is a linear piecewise function. It's not a pure linear function, but it's a piecewise function, and all of the parts, all the intervals are linear. They're straight lines. And this one is, I guess technically it's nonlinear, but some may argue, well, wait a minute, what about that spot right there? We're looking at a linear portion, but then there's other parts, other intervals of change, and you can see that through here and from here to here. You've got these other parts that are not linear or nonlinear. Alrighty, well, that's about it. Hopefully you can use this to work on the assignments, and as always, reach out to your teacher, go to the tutoring room, get that extra support, and good luck with analyzing piecewise functions.